So, hello everyone. I hope I'm audible and visible. So, let's wait for 5 to 10 minutes so that everyone can able to join the session. So, okay, everyone, let's start the session. I hope I'm audible and visible. So, hello everyone, a very good evening to one and all of you. So, my name is Pooja Verma. I'm PMR Research Scholar from IIT Kharagpur. And instructor for this course is Professor Samal Kumar Das Mandal from Advanced Technology Development Center, IIT Kharagpur. This is a week 9 live and interactive session on signal processing techniques and its applications. So you can use chat box for asking and interacting. Otherwise, you can also unmute yourself and ask your doubts and questions. So this is week 9. So I hope all of you have gone through this week video lectures. So regarding this week, the course content is design optimum equiripple linear phase FIR filters. That is optimization methods. And next one is infinite impulse response filters, traditional analog filter design, Chebyshev filter design method, analog filter to digital filter transformation. Okay, so these are the contents which have been gone through this big video lecture. So first we will see some theoretical concept, then we will solve some questions or some problems which is very similar to your assignment problems. Okay, so first one is infinite impulse response filters, that is IIR filters. So what is the IIR filters? So IIR filters we will use when speed is important and phase nonlinearity is acceptable. Okay, so IIR filters are computationally more efficient than IIR filters as they require fewer coefficients due to the fact that they use feedbacks and poles. Okay, so general equation for IIR filter design is this, that is V0 plus h of z is equal to B0 plus B1 z inverse plus till Bn z to the power minus n. Then in the denominator, that is 1 plus A1 z inverse plus till Am z to the power minus m, where m is the number of poles and n is the number of zeros, total number of zeros. Okay, in the compact form, we will represent the IIR filter in this form, that is Vk z to the power minus k, where summation will vary k is equal to 0 to n, and in the denominator, that is it is written like this 1 plus in that form, because we will use feedback, or we will get only poles. That's why it is written in this form, so that we will able to calculate poles, or we will able to use in the form of feedback. Okay, now next one is analog to digital filter conversion. There are two principal methods that have been used to analog to digital filter conversion. One is a bilinear transformation and another one is impulse invariance method. Okay, now traditional analog filter design, there are three basic main traditional analog filter design, that is a Butterworth filter design, Chebyshev and elliptic filter design. Mostly we will use these two. Okay, so Butterworth filter design, this is a basic magnitude squared frequency response for a low pass Butterworth filter design. This is a basic equation, 1 divided by 1 plus e square, that is epsilon, uh, multiplied omega by divided by omega p to the power n, where n is the number, order number. What is the order of that filter? Okay, where e, that is epsilon, is represent the ripple factor, and omega is the 3 dB cutoff frequency. It is a pass band cutoff frequency. Okay, and then order of the filter n can be derived by this equation. N must be greater than equal to log in bracket 1 by del s minus 1 divided by 2 log omega s divided by omega p, where it is a cutoff frequency in the stop end and omega p is the pass band frequency. It is a pass band frequency. Yeah. Now next one is Chebyshev filter design. So Chebyshev filter design is based on Chebyshev polynomials, and there are basically two types of filters that have been designed, that is Chebyshev 1, type 1 Chebyshev filter, and type 2 Chebyshev filter. So this is a Chebyshev type 1 filter, and the characteristic equation is represented by this. Okay, 1 divided by root of 1 plus epsilon square Tn square omega divided by omega p. Now this is a Chebyshev 2 filter, and their frequency response characteristic defined by this equation. And for nth order Chebyshev polynomial, the order of the filter is defined by this equation. Okay, so we will use while we will solve the problems. Okay, that is n is equal to log in in numerator in brackets 1 minus del 2 square plus root of 1 minus del 2 square 1 plus epsilon square in bracket divided by e del 2, and in denominator log in bracket del omega s divided by omega p plus omega s divided by omega p whole square minus 1, and it is equal to cos hyperbolic inverse del of e divided by cos hyperbolic inverse omega s divided by omega p, where del 2 is defined is calculated by this equation. Okay, so now next one is a IR filter design. So there are two types of IR filter: impulse invariance method and bilinear transformation. So how we will calculate using the impulse invariance method. So design an IR filter having a unit impulse response h of n, that is a sampled version of impulse response of analog filter, that is HA of t. So it is represented by this, and HA of s is there is Ck divided s minus Pk, that means number of poles where k varies 0 to n, and n is the order of that filter. So it is varies from k is equal to 1 to order of that filter, and it is then Ck is defined by, already we know that how to h of s minus Pk at s is equal to Pk. After that, then overall that function is represented in the Z transform, that is k varies 0 to n Ck 1 divided by 1 minus e to the power Pkt Z inverse. Okay, after getting all those things. Now next one is a bilinear transformation. So mapping from S plane to Z plane, we use bilinear transform also. So basic principle is application of trapezoidal formula for numerical integration equation, differential equation. So transfer function of any analog filter is defined by this. For example, HA of S equal to B divided by S plus A, and the transfer then we will determine in the digital form, that is H of Z B divided by 2 by T 1 minus Z inverse divided by 1 plus Z inverse plus A. That means in the place of S we are placing this equation. So this is a conversion factor S to Z domain, that is mapping from S plane to Z plane, and consequently we can design from we can get the Z value from this equation. Okay, and omega we can determine by 2 arctan omega t divided by 2, and omega is it is a digital domain frequency, and it is already we know the analog domain 2 by t tan omega by 2. Okay, so this is a basic information that we will use while solving our problems. Okay, now we will move to the questions. First question is the advantage of optimum equiripple linear phase FIR filter is. What is the advantage of optimum equiripple linear phase FIR filter? Option A is simple techniques to design linear phase FIR filter. Option B, precise control for critical frequencies. Option C, both A and B, and option D is none of the above. So which option may be a correct one? So if you have gone through this week video lecture, so I think you will see this one is the first, or in the first slide itself, that is the advantage of optimum equiripple linear phase FIR filter is it has a precise control of the critical frequencies. So option B is the correct answer for this question. The detailed explanation is given in the next slide, that is in the context of a FIR filter design, while both the window method and frequency sampling method offer simpler approaches, design linear phase FIR filters, they lack precise control over the critical frequencies such as a pass band edge and stop band edge. So the limitation can be significantly disadvantaged in application where exact specification of these frequencies is crucial. So optimum equilibrium linear phase FIR filters provide a method where such precise control is achieved, making them highly desirable for more demanding filter design coefficient, where precise cutoff frequencies are essential. So that's why option B is the correct answer for this question. Okay. Okay. So I hope you are getting. So moving to the next question. Now next question is, given the specification that is alpha p is 1 dB, alpha s is 30 dB, omega p is 200 radian per second and omega s is 600 radian per second, determine the order of the filter. How we can determine the order of that filter? So here given alpha p, alpha s, omega p and omega s. So to determine the order of that filter, the formula is can be determined order of filter n must be greater than equal to. Here the filter which filter design has been used, it is not which method we have to not define, so you can use any one and check cos hyper because also check that these what the values are given. Based on that you have to choose the which formula you have to use. Okay, so here I am using because these values are given, so that's why. So formula is 10 to the power 0.1 alpha s minus 1 divided by 10 to the power 0.1 alpha p minus 1. Okay, and whole divided by cos hyperbolic inverse omega s divided by omega p. So by using this formula we can calculate these values. Okay, so that is n must be greater than equal to, always remember. Okay, so just put all these values. So cos hyperbolic inverse in bracket 10 0.1 into alpha s. Okay, that means 30 sorry minus 1 and then divided by 10 to the power 0.1 alpha p is given as a 1 dB, so 1 minus divided by that. So cos hyperbolic inverse omega s is given 600 radian per second and omega p is given as a 200 radian per second. Now if you further calculate it, so here so much calculations are needed, so I will request all of you, please carry one calculator while solving these problems. Okay, so cos hyperbolic inverse, so if you just calculate it, so you will get in the upper side, if you calculate it, 3857.14. In the lower side you will get 0.126 divided by, that is cos hyperbolic 3. Okay, that is. Now if you further solve it, you will get cos hyperbolic inverse, the value you will get 62.175 divided by cos hyperbolic inverse. Now from the calculator you directly calculate these values, you will get 4.822 divided by 1.76. If you further calculate divide it, you will get 2.73 6. So n, what you will get, that n must be greater than equal to 2.736. That means approximately equal to 3, right? Approximately equal to 3. So that's why option D is the correct answer for this question. Okay. Okay. So I hope you understand this question. So moving to the next question. Okay, so next question is, poles of a Butterworth filter lie on an ellipse. A is true or false? This content is true or false. Poles of a Butterworth filter lie on an ellipse. So this statement is false because the poles of a Butterworth filter don't lie on an ellipse. They lie on a circle. Okay. The poles of a Butterworth filter lie on a circle. Okay. So Butterworth filters are known as a maximally flat magnitude filter, are characterized by having all their poles evenly spaced along a circle in the left half of the complex plane. Thus, this circular arrangement ensures that the frequency response is as flat as possible in the passband without any ripple, so leading to the alternative name maximally flat magnitude filter. So this statement is false. The poles of a Butterworth filter lie on a circle. Okay. So the poles of Butterworth filter lie on an lie on circle. Okay. So now next question is, in bilinear transformation of the left half S plane is mapped to the which of the following in the Z domain? Option A is entirely outside unit circle, that in mod of Z is equal to 1. Option B, partially outside of the unit circle, Z is equal to 1. Entirely inside the unit circle, that means this is unit circle, and partially inside the unit circle. So in the bilinear transformation, the left half of S plane is mapped to the which of the following domain? So this is a S domain, right? And this one is a Z domain, where Z is equal to 1, and this one is S sigma, it is a, sorry, J omega, it is a sigma. Okay. So that left of the side, whatever pole which will go through the inside the circle. If the poles are right sides, already we know that, that means system is unstable, that will lie outside the unit circle. Okay. If poles are on the imaginary plane, then it is equal to that one. So in the bilinear transformation method used for a digital filter gen, the left of the S plane is mapped to the inner inside unit circle Z in the Z domain. This transformation preserves the stability of the analog filter when converting them to the digital filter, as the poles of the left half plane stable in the analog domain are transformed into the Z domain to the inside unit circle. So that's why entirely inside unit circle. That is option C is the correct answer for this question. Okay. If poles are on the j omega axis, so that will plane exact this case. Okay. So okay, I hope all of you are getting. So moving to the next question. Now next question is, low pass Butterworth filters are also called as, option A is all zero filter, option B all pole filter, or option C pole zero filters, or D none of the mentioned above. So low pass Butterworth filters are also called as a, what they have called as a, So low pass Butterworth filters are characterized by their smooth, flat frequency response in the pass band and lack of ripple. They achieve this response primarily through the placement of the poles and does not use zeros to shape their frequency response. So they are all pole filters. Okay. So this describes filters that utilize only poles in their transfer functions without incorporating zeros. They to alter the frequency response. So Butterworth filter, all low pass Butterworth filters are called as a all pole filter, also called as a all pole filter. Okay. Okay, so I hope you are getting. So moving to the next question. Now next question is design Butterworth filter using impulse invariance method for the following specification. So this specification is given. Now we need to design a Butterworth filter using the impulse invariance method. Okay, so how we can solve this question, this problem? Anyone of you have any idea? Okay, so let's solve that. Given that this is given, okay, so first we will see what are the parameters that have been given. So mod of h of e j omega is given, that is vary from 0 to 8, 0.8 to less than 1. So we will equal to, so we can take 0.8. So that means 1 divided by 1 plus epsilon e square given as 0.8. Okay, from here you calculate this value epsilon. So from here you can directly take it, sorry, root of. Okay, so 1 plus e square you will get 0.64. From here if you calculate it, you will get 1 plus e square divided by 1 divided by 0.64, and that is equal to e square you will get 0.5625, and similarly e you will get 0.75. Okay, similarly we have to calculate lambda value also. So 1 divided by 1 plus lambda square is equal to 0.2 is given. Okay, here you can say 1 is 0, omega varies 0 to 0.2 pi. That in that time the magnitude of that Butterworth filter will vary from 0.8 to 1, and after 0.6 pi to pi, till here the magnitude will be less than equal to 0.2. Okay, so here less than that is not defined, so that is equal to, so that's why we are taking the 0.2. Okay, similarly from here also you will get 1 plus lambda square is equal to 0.04, and 1 plus lambda square, if you further calculate it, you will get 25. Okay, from here lambda square will you will get 24. If you further solve it, you will get lambda is equal to 4.899. Okay, so now we have got epsilon value. Okay, that is e is equal to, that is how much we have got, 0.75. Lambda we have got, that is 4.899. Okay, now from here we can calculate also the cutoff frequencies of that Butterworth filter. So what will be the omega s? Omega s, that is the stop band frequency here. So till here it will pass. So stop band frequency is equal to 0.6 pi. And what will be the pass band frequency? So past till here that will pass the frequency 0 to 2 pi. So 0.2 pi is the pass band frequency. Okay, and assume here t is equal to 1. Assume t is equal to 1 second. Okay, now I am removing it from here so that we can solve the problem. further. So okay, so these values we have calculated, right? Now we have to calculate the, these are the analog frequency. Now we have to calculate the digital frequencies, right? And order of that filter, how we can calculate it? So already we know that omega s divided by omega p is equal to omega s into t into omega p into t, right? Similarly, t is equal to 0, so that will be the same only. So omega s divided by omega p is equal to 0.6 pi divided by 0.2 pi. Okay, from here you will get 3. Now we need to determine the order of that filter, Butterworth filter. So formula from here is log lambda divided by E divided by whole log omega s divided by omega p. Okay, so here, so already all these values we have calculated, that is lambda value is 4.899 and E is 0.75 divided by log omega s and omega p is 3, so log 3. Okay, now if you calculate it, then n value you will get, and must be 1.71, that is equal to 2. That means one n value we have got 2, right? The order of the filter we have calculated, that is 2. So the order of that filter, it is, we can modify it like whatever values we have given, based on that we can calculate it. All these formulas you will get. Okay. Okay, so now order of that filter we have got. Then what will be the transfer function of that Butterworth filter based on these parameters? So from the equations already given, what is a standard transfer function of the Butterworth filter? So from here you will get the transfer function of the normalized Butterworth filter will be the transfer function of Butterworth filter h of s we can define as a 1 divided by s square plus root 2, that means root n s plus 1, that is the order of that filter. Okay, and also we need to determine the cutoff frequency. Okay, because here we will use omega divided by omega p. Okay, so cutoff frequency, that is omega c. So omega, it is a pass band frequency divided by epsilon 1 by n. So omega p already we know that, that is 0.2 pi and 0.75 1 by 2. If you further calculate it, you will get 0.23 pi. Okay, or 231 pi. So cutoff frequency omega c is equal to 0.231. So all these values we have to calculate while we are designing the Butterworth filter using the impulse impedance method. Okay, so please carry one calculator, otherwise it is very hard to calculate. So I have calculated all these values before I have solved it. So otherwise in that class it is not possible to calculate as well as uh, do that. Okay, okay, so all of you please carry a calculator and try to calculate all these values with me. Okay, so this is a transfer function we have got. So how we can convert from the analog to digital domain, that is h of s, where s we can put s by omega c. Okay, in the place of s we also we have to take the cutoff frequency and under consideration, right? Now we need to put we need to determine HA of S, that is a Butterworth filter. So 1 divided by, we have to put S divided by omega C whole square plus root 2 S divided by omega C plus 1. Okay. Now further we will solve it. We will get omega C square S square plus root 2 omega C S plus omega C square, right? Now put the value of omega C in this equation, then you will get, so I can remove it from here. So from that, I think you all have noted down, so I'm just removing it so that we can able to write down. Okay, so this equation we have got. Now put the value of omega C in all equation and now calculate it. Okay, so HA of S is equal to 0.231 pi, so it is pi also. Oh, here pi also is there, right? Square divided by S square plus root 2 into 0.231 pi S plus 0.231 pi square. Okay. Now if you further calculate all these values, you will get 0.526 in the numerator, then S square plus 1.026 S plus 0.526. Further, if you do multiplication of all those values and calculate all these values. Now, what you need to do? Now you have to factorize the poles. Okay. Now you have to factorize this pole. Okay. This one is S. So in order to getting the poles, already you know that just take a factor. So further, if you factorize it, you will get 0.526. The denominator will be the same. Now first we have S plus 0.51 plus J 0.51. Okay. Now next pole is S plus 0.51 minus J 0.51. Okay. So these are the two poles. So now it is, we can write it in that form. In order to get all the A divided by S plus with this pole 0.51 plus J 0.51 plus B divided by this, then this one here, right? Okay, so I'm just removing it from here, all those things. Now just calculate the values of A and B, or you can like say that already we know that in the impulse invariance method, HA of S, impulse invariance method, that is K vary from 0 to N, that is Ck S minus Pk. So we have to put it in that form. So here N is equal to 2 and also poles we have got 2, right? So if we N will be to C1 S minus P1 plus C2 here S minus P2, right? So from here A and V value, A is equal to C1, V value is equal to C2 and that poles. Okay. Now if you further just convert it into a Z domain, so already we know that what is the value? K varies from 0, 1 to 2, that is Ck 1 minus e to the power pkt, that means one pole, poles Z inverse. Now, if you calculate the values of A and B here and or C1 or C2, then you will get, so just have you calculated from there? So we have got that equation, right? Just a minute. We have got that equation. That means I am just placing in place of A is C1. Okay, C1 S minus 0.51, sorry, plus J 0.51 plus C2 S plus 0.51 minus J 0.51, right? So if you just calculate C1 value, you will get J 0.516, and similarly C2, if you calculate it, you will get J 0. Both values are same. Okay, now just put all those values in that Z transform equations. Okay, so in this equation, just I'm writing here. So you have got the C1 and the C2 values. So just a minute, it is not. Okay, so already we know that h of z, how to calculate. H of z is equal to k varies 0 to 2 ck 1 minus e to the power pkt z inverse. If you further just you will get like this. So these are the poles. So poles is these are. So from here we can write it directly. J 0.516 divided by 1 minus e to the power pkt, that means that these poles. So minus 0.51 minus J 0.51 Z inverse. Similarly, for it is, you have got it G minus, that is okay. So minus J 0.516 divided by 1 minus e to the power minus 0.51 plus J 0.51 Z inverse. Okay. So calculate the value of e to the power minus 0.51 minus J 0.51 and put it there, and also calculate these values and then cross multiply it. Okay, so further by solving you will get 0.3022 divided by 1 minus 1.047 Z inverse plus 0.36 Z to the power minus 2. Okay, so if you further just calculate it, you will get these values. Okay, so from here you can check which option is correct. So this is the whole method to how to solve this type of problem. Okay, so just match 0.3 0.3022 divided by 1 minus 1.047 Z inverse plus 0.36 Z to the power minus 2. So from here option D is the correct answer. Okay, so just there are some confusing points are there, because here they have used plus minus, then plus plus, then minus minus, then minus plus. Just remember these notations. Okay, so option D is the correct answer. Okay, so I hope you have understand so how to solve this type of problem. Now moving to the next question. Okay. Mm, just a minute. Mm, just a minute. I'm not able to just remove it. So it is not removing. Okay. So just I have to close it and then again open it. So just wait for 2 minutes. Okay, sorry for the interruption. So just a minute. So till question number 6 we have solved. So now moving to the next question. Okay. So now next question is also that question also. So design a Chebyshev filter for the following specification by using the bilinear transformation. Okay. So here what we have used the impulse invariance method to solve this problem. Here now the same problem we need to use using the impulse invariance method. Okay. So now already we know that we have calculated the epsilon and that lambda value. So from there I am directly writing it. We are not going to calculate 0.75. We have got lambda value, we have got 0.899, right? In the previous question we have solved. So now it is a bilinear transformation. Okay, now we have to determine the digital frequencies. How? That is like this: omega s divided by 2 tan omega s divided by 2, right? So now omega s is equal to 2 tan omega s. We know that omega s is equal to 0.2 pi, right? No, 0.65 the value, and omega p is the 0.2 pi, right? So omega s is 0.6 pi, so 0.6 pi divided by 2. If you further just solve it, 2.752 you will get. Similarly, you have to calculate the omega p also. So 2 tan omega p divided by 2, that is equal to 2 tan omega p is 0.2 pi divided by 2. Now, if you further calculate it, you will get 0.6498. Okay. So, omega s and omega p you have calculated. Now, first we need to determine the order of the filter. So, that formula is cos hyperbolic inverse lambda by e divided by cos hyperbolic inverse, that is omega s divided by omega p. Okay, so just putting all those values, already we know that cos hyperbolic inverse, that is lambda is 0.899 and 0.75 divided by cos hyperbolic inverse omega s is 2.75 divided by 0.6498. Okay, just calculate all those values by calculator. So you will get that is 1.208. Okay, the order of the filter you will get 1.208. Okay, so from till here we have calculated. Now next what we need to do, so just remember all those values. Now in order to calculate further, we need some more parameters. Okay, so just mu already we need to calculate the value of mu. Okay, so mu formula to calculate mu is epsilon inverse plus the mu is the parameter that we need to calculate the uh, some values, that is a and b, some constant values. Okay, so that's why we will I will let you know. So this is the formula. Just put the value of epsilon here. So that is 0.75 inverse plus root 0.75 minus 2 plus 1. If you further just calculate it, you will get approximately 3. The value of mu you will get 3. Okay. Now where we will use that mu? In order to find out the constants. Okay. When we need to determine the poles, then we will use all those things. Okay. So A is equal to omega p mu 1 by n. Here A and B are the constant values of the poles and zeros will be there. So mu 1 minus 1 by n. Okay, and divided by 2. Okay, now put the value of mu here. So omega p already we have calculated, that is 0.6498, and just put the value of n. Mu is 3. So 3 to the power 1 by n. Okay, that n value is 2, approximately 2, right? 1 by 2 minus 3 minus 1 by 2 divided by 2. Now further just calculate it, all those values you will get, that is a you will get 0.6498. 3 to the power 1 by 2 you will get 1.732 minus 3 to the power minus 1 by 2 you will get 0.577 divided by 2. Okay, just divide, multiply, divide, you will get 0.3752. Okay, so here A we have got 0.3752. Now similarly we have to find out the value of B. So formula for B is mu value is 3. Okay, and n value what will be derived is 2. Okay, similarly we have to calculate the value of B. So just I'm removing it from here because we have noted down. So B similarly we have to derive for B also. What is the formula? B is same mu p. Here it is a mu is equal to 1 by n here, but it is plus mu minus 1 by n. All those things are same. So further just putting all those values, you will get p is equal to 0.75. Okay, just calculate it, 0.75. Similarly a, okay, but here it is minus, here it is a plus. Okay, so just calculate it. Now next one is to find a poles and zeros, because we need to find using bilinear transformation to find poles and zeros. So Sk, where S is the poles. Okay, so Sk is the, K varies from 1 to n. So A cos phi k plus J B sin phi k, where k varies from 1 to n. N is in order of the filter. So n is 2, that means it will vary to 1. K will vary to 1 and 2. Right? Now how you will calculate that phi k? For phi k the formula is pi by 2 plus 2k minus 1 divided by 2 and pi, where k will vary same. Okay, now first we will get phi 1. Phi 1, put k is equal to 1, so pi by 2 plus 2 minus 1 divided by 4 pi. Right, so here it is a pi by 2 plus pi by 4. So equally we will get 3 pi by 4. Similarly, you have to calculate phi 2 also. So pi by 2, just putting k is equal to 2. So 4 minus 1. So 3 pi by 4. So that is equal to 5 pi by 4. Right? Now, first we have to take first pole, then second pole. So phi 1, phi 2 we have calculated. Now put k is equal to 1. So if we are putting k is equal to 1, so S1 we have got A value and V value we have calculated. So I'm just writing A cos phi 1 plus J B cos sin phi 1. Okay, so just putting all the A is 0.375, cos uh, phi 1 value is 3 pi by 4, right, plus J, B value is 0.750 sin pi 1 is 3 pi by 4. Okay, now if you further just get cos 3 pi by 4 value and sin 3 pi by 4, put and multiply by it, you will get the value minus 0.2653 plus j 0.53. Okay, similarly you can get the value of, similarly you can derive S2. So S2 you will get A cos phi 2 plus J B sin phi 2. Okay, so you put the values of A, B and phi 2. So A is already, we know that 0.752 cos 5 pi by 4 plus J, in multiplication I'm writing here. Okay, just 0.75 sin pi 5 pi by 4. Okay, so I'm just removing it from here. So I'm directly writing the values. So just you calculate it. Okay, so just if you just put and multiply and divide it, you will get minus 0.2653 minus j 0.53. Okay, so these are the poles. Now, so poles we have defined and we have got, okay. So just I am removing it. I hope you have noted down. So, okay, so I'm just remove, okay. So you can see it from the YouTube video. So poles we have calculated. Now we have to design the transfer function. Okay, that is transfer function from the given information. Transfer function, that is h of s. So if you further just put, that means something is there, 1 divided by the poles s minus, so s1, right? So just s1, what is the value? That is 0.2, here it is a plus, 0.26 minus j 0.53 s1 pole, and similarly for s2, s plus 0.2653 minus j 0.53, right? Now further, just if you just resolve it and divided by 1, a and b, just getting the constant, then you will get the final transfer function. You will get 0.28 divided by s square plus 0.53 s plus 0.3516. The final transfer function after divide and just getting the constants, you will get this function. Okay, so now we know that how to do the bilinear transformation. So bilinear transformation, we know that just putting h of z is equal to h of s, just put in the place of s, that is s is equal to 2 by t 1 minus z inverse 1 plus z inverse. In place of s, just put these values. Okay, and then just divide and multiply it. Okay, so just I'm going to put in the place of s these values, then we will see. So here you will get 0.28, s is equal to, that is 2 by t. So t is 1, we have taken in the previous itself. So okay, so yeah, so s square, that means 2 1 minus z inverse divided by 1 plus z inverse whole square. T is 1, right? We have taken in the previous, plus 0.53 multiplied by s, that means in bracket 2 1 minus z inverse divided by 1 plus z inverse, okay, plus this value plus 0.3516. Now what we need to do, just I am removing it from here, otherwise we can't calculate it. Okay, now just 0.28, just taking 1 plus z inverse square divided by 4 1 minus z inverse square, right? 2 2 ja 4, 1 minus 9 plus 0.53 into 2. So now if you multiply it, you will get 1.06, right? 1.06 1 minus z inverse 1 plus z inverse. Okay, so here 1 plus z inverse square, so 1 plus z, when it is 1 plus z inverse and 1 plus 1 cancelled out and 1 will be here. Okay, plus 0 0.3516 1 plus z inverse square. Okay, this is a whole part. Now if you further just divide and multiply and do the calculation, you will get 0.28 1 plus z inverse whole square divided by, just multiply all those things, open the, then take all those things, you will get 5.4128 minus 7.298 z inverse plus 3.29 z to the power minus 2. Okay, you will get all those. So which option is the correct one from here? 0.28 1 plus z inverse square minus then plus. So option D. Option D is the correct answer here also. Okay. So here option D is the correct option. Just we need to solve like this. Okay. Now I hope you have understand. Just take one calculator and sit always go step by step and calculate all those values. Okay. So moving to the next question. Now next question is, the Chebyshev filters have the one is passband, flat passband, on option 2 is flat stop band, 3 is equiripple passband, and 4 is tapering stop band. So which option is the correct one? Option A is 1 and 2 are the correct statement, or option B is 2 and 4 are the correct statement, option C is 2 and 3 are the correct statement, and option D is all of the 4 are the correct. So in the Chebyshev filter already we have given one explanation also. So option C 2 and 3 flat stop band and equiripple pass band. In the Chebyshev filter there is a pass band, stop band and equiripple pass band. So that's why option C is the correct answer for this question. Okay. Okay, so I hope you understand. So now moving to the next question. So now next question is also related to the IR filter design using the bilinear transformation. Okay, so question is, convert the analog filter with given system function into IR design filter by means of a bilinear transformation. So digital filter have a resonance frequency, that is omega r is given as pi by 2. So h of here transfer function is given, h of s is equal to s plus 0.1 divided by s plus 0.1 square plus 16. Okay, so by using the bilinear transformation we have to design a digital filter. Okay, so just first see the cutoff frequency here. So omega square, already we know that omega square is equal to 16. So omega will be the 4. Okay, from that the equation, and also we know that in the bilinear transformation, and we know that it is a bilinear transformation, so all the frequency, we know that omega is equal to 2 by t tan omega by 2. So omega from here we have calculated, so 4 2 by t tan, here the resonance frequency is given, that is omega r. So here just take it, so pi by 4. So pi by 4 value is 1. So from here t calculated, that is 2 by 4, that is 1 by 2 equal to 0.5. Just calculate the value of t. Now further, in the place of s to z conversion, we know that here it is a 2 by t 1 minus z inverse 1 plus z inverse we have to put. So just eat the whole equation 1 minus z inverse divided by 1 plus z inverse. Now put this into the in place of s, right, in order to convert into the z transform. Okay, I don't know. So just from here we will put the values. In place of s we need to put, okay, h of z. So in place of s we need to put these values. So 4 1 minus z inverse divided by 1 plus z inverse plus 0.1 divided by s means 4 1 minus z inverse divided by 1 plus z inverse, right, plus 0.1 whole square plus 16. Okay, now further calculate it. So just hmm, so just put open in the denominator part first. So I'm just taking 1 minus z inverse divided by 1 plus z inverse plus 0.1. I am taking numerator as it is and open the denominator because it is a whole square. So a square whole square a plus b whole square. So a square plus b square plus 2ab. Already we know that. So just take it here. So 16 1 minus z inverse whole square 1 minus 1 plus z inverse whole square, right, plus b square, that means 0.1 square, that is 0.01 plus 2ab. So 2a and b. So 8 into 0.1. So 0.8 it is. Okay, it is a 0.8. 1 minus z inverse divided by 1 plus z inverse plus 16. Okay, this is the whole denominator part. So just I am removing it so that I can write it down. So you have opened. So just it is in the denominator. So we can multiply it further if you take it. Further solve it. So 4 if you go. So here it will left 1 minus z inverse 1 plus z inverse, right? Because 1 plus z inverse will be cancelled out. So 1 is in multiplication plus 0.1 1 plus z inverse whole square will be in the numerator. Now in the denominator what left, that is 16 1 minus z inverse whole square plus here just add this because nothing is there. So 16.001 or we can take it 16.01 approximately equal to 16. Okay, plus 0.8 1 minus z inverse into 1 plus z inverse. Okay, this is the denominator part and numerator part after solving all those things. So just I am removing all those things so that I can just you can solve it by seeing the video. Okay, so now h of z we have just we need to take the calculations. Okay, so here it will left z 1 minus z to the power 2. If you just multiply 1 minus z inverse and 1 plus z inverse, that will you will get plus 0.1 1 plus z inverse whole square. So 1 plus z to the power minus 2 plus 2 z inverse, right? Similarly, if you in the denominator you will open it, we will get 1 minus z to the power minus 2 minus 2z inverse plus 16.01 1 plus z to the power minus 2 plus 2z inverse, okay, and plus 0.8 1 minus z to the power minus 2. Now further if you solve it, you will get here, if you just multiply and 4, here 1 and 1, so just we can add it 4.1, right? Now 4 minus 4 z to the power minus 2 and 0.z1, so here you will get minus minus 3.9 z to the power minus 2 plus 0.2 z inverse. Just open it, multiply inside that and open it, add it, you will get. Similarly here if you do that, so 16 and 16, that is 32, so 0.01 I am removing, okay, 32 plus here, no, 32 plus 0.8, so 32.08, okay, all the constant parts I am adding now, where z to the power minus 2 is there, okay, so z 16 z to the power minus 2 and 16 z to the power minus 2 and minus 0.8 z to the power minus 2. 16 and 16 is 32. 32 minus 0.8, you will get 31.2. That, yeah, 31.2 z to the power minus 2. Now z to the power minus 2 term will be, so 16 into 2 z inverse and 16 in plus z, so that will the cancel out this one and this one, right? So this will left here. Now normalize the numerator and denominator, because in the denominator we have to take in that form 1 plus form, okay, so just divide it by in the numerator and denominator by 32.08, divide by 32.08 to normalize the transfer function, to normalize the transfer function. So if you just divide it, you will get, so I'm just writing it here. So from here, so I'm writing here the final transform h of z is equal to, if you just divide by 32.08 in the denominator and numerator, you will get 0.128 minus 0.06 z inverse minus, sorry, here it is plus, minus 0.122 z to the power minus 2, okay, and here similarly 1 plus, if you just do the 0.975 z to the power minus 2, okay, you will get. So already we know that these are the poles, and in the upper part that are the holes, sorry, poles and zeros. So just put poles are equal to 0 and zeros are equal to 0, then you will get the poles and zeros. So poles, so 1 plus 0.975 z to the power minus 2 is equal to 0. Now if you further solve it, you will get z square is equal to minus 1 divided by something, z square, so here it is minus 0.975. If you further just solve it, you will get plus minus 0.987, it minus in the place of -1 you will get plus minus j pi by 2. Okay, similarly for zeros, just put equal to 0 and just find out the zeros. So zeros you will get, here it is a poles, here it is a zeros, that is Z12, here it is a poles. Okay, so just by we will get minus 10 to the minus 9 5. Okay, so this is the final transfer function. These are the poles and zeros. Just put poles equal to zeros and poles equal to 0, that means the denominator part equal to 0 and numerator part equal to 0 to get the zeros, and find out uh, the z values. Okay, so from here if you see that the correct answer is minus 10.95 and 0.987 e to the power. Okay, so option A is the correct answer for this question. Okay, if you solve it properly. Okay, so are you getting? Okay, so moving to the next question. So next question is, which of the following filter transformation is not possible? So option A is high pass analog filter is to low pass digital filter, high pass analog filter to high pass digital filter, or option C is low pass analog filter to low pass digital filter, or none of the mentioned above. So which of the following transformation is not possible? So already we know that only low pass and band pass filters with low resonant frequencies in a digital can be designed. So it is not possible to transform high pass analog filter into a corresponding high pass digital filter. So option B is the correct option. So high pass analog filter to high pass digital filter design is not possible. Okay. So I hope you are getting. So moving to the next question. Now next question is, which of the following methods are used to convert analog filter into a digital filter? So analog filter to digital conversion, digital filter conversion. So option A is approximation of derivatives. Option B is bilinear transformation. Option C is impulse invariance transformation. Option D is all of the mentioned. So already we have seen in the previous slide and in the video lectures also, bilinear transformation and impulse invariance are used to convert the analog to digital filter conversion, and also approximation of derivatives also used to convert analog filter into a digital filter. All of the above are the correct option for this question. Okay, so just check option by option, what are the given, based on that you have to choose the correct option. Okay, so I hope you are getting. Now moving to the next question. Okay, so next question is, pole zero placement method is used to design a IR band pass filter with the following specification. Okay, if the poles of the filter represented by r e to the power j theta, determine the value of r and theta. Okay, signal rejection at zero frequency is 400 Hz, a narrow pass band centered at 200 Hz, 3 dB bandwidth of 60 Hz, and sampling frequency is 800 Hz. So these are the parameters which have been given. Now we have to determine the value of r and theta. Okay. Okay, so already we know that zeros are placed at the angle of signal rejection at zero frequency is 400 Hz. So in any IR filter, zeros are are placed at angle of 0 and 2 pi, that is signal rejection at zero frequency, and divided by the sampling frequency. That means I just F0. I'm just writing. So 0 is 1 and another is a 2 pi into 400 divided by 800. So 2 and pi. So zeros are placed at the angle of 0 and pi. Okay. So 2 have pass band and centered at 200 Hertz. Poles should be placed at poles should be placed at plus minus 2 pi into pass band centered frequency divided by pass band centered frequency divided by sampling frequency. So that is, if you calculate plus minus 2 pi, Fp is 200 Hertz divided by 800. So 4, that means poles should be placed at pi by 2. That means plus minus pi by 2. Okay. So now further, so poles and zeros are placed at which frequency we have got? Should be placed at an angle. So zeros are placed 0 and pi. Zeros are placed at 0 and what we have calculated pi. And then we have to remove it from here. Okay. So we have just and poles are placed at plus minus pi by 2. Poles are placed at plus minus pi by 2. We have determined. So to have a real coefficient, the poles should be complex conjugate of. To have real coefficients, poles should be complex conjugate of conjugate at R is equal to e to the power minus bk. Okay, now how we determine the bk? So bk is equal to pi by fs, that is sampling frequency, into band width. Okay, so pi divided by 800 hertz into bandwidth, what is it? 60 hertz into 60. So 6, we cancel out, we will get 0.225. Just put all value of pi and just divide it. And what will be the value of ER? E to the power minus 0.225. So you will get 0.798 if you calculate it. Okay, so R value we have got 0.798 and theta value, that means the theta is, what is the theta? If the poles of the filter represented are e to the power r and theta value. So poles should be presented at plus minus pi by 2. Okay, so theta is centered at 200 frequency. Theta k will be equal to pi by 2, because that if the poles of the filter represented by, so the poles are presented at theta is equal to plus minus 2. So here no, so R value we have determined, that is 0.798 and theta is pi by 2. Okay, so option C is the correct answer for this question. Okay, okay, so I hope you have understand. So moving to the next question. Now next question is, determine the order of the low pass Butterworth filter with maximum gain of 10 dB and a cutoff frequency of 2 kHz at which the gain is at least 7 dB and stop band frequency is given 4 kHz at which magnitude it is required to be less than minus 30 dB. So here we need to determine the order of the low pass Butterworth filter. So just let's given, what are the given data? Given that is omega p is equal to 2 kilohertz and omega s stop band frequency is 4 kilohertz. 3 dB down, so 3 dB down, here it is, so that is E must be equal to 1. Okay, so total attenuation, what will be the equal to minus 30 and maximum gain, that is minus 10, equal to minus 40 dB. So now minus 40 dB total attenuation is equal to, if we just do that, 20 log del 2. So from here if you calculate it, 2, so 10 to the power minus 2 will be there, right? So that is equal to 0.01. Now the order of the Butterworth filter, that is defined by n, is must be equal to, we know that formula, log 1 minus del 2 square minus 1, right? 2 log omega p divided by omega s. Okay, now put the values. So log 1 by del 2 means 10 to the power minus 4, it will be the 10 to the power 4, right? Minus 1 divided by 2 log omega p is 2 divided by 4, right? Sorry, omega s divided by p होता है. So 4 by 2. Now if you just calculate by what is the value of 10 to the power 4 minus 1 and 2, so you will get 13 divided by 2 and log base 2 will be 2, so you will get directly 6.64, that is approximately equal to 7. Okay, so the order of the filter is 7. So option A is the correct answer for this question. Okay, okay, so I hope all of you are getting, so I am a little bit quick. So just I have solved this question, so just take one calculator and calculate all those values, so it is better. Okay, okay, so I hope you have understand. So moving to the next question. The next question is, determine the order of the type 1 low pass Chebyshev filter that has 1 dB ripple in the pass band, cutoff frequency is given 1000 Hz, stop band frequency is given 1500 Hz, and attenuation of 40 dB or more. Okay, so the given values, the values are given. So cutoff frequency, stop band frequency, and attenuation in the pass band and stop band. So from here we can directly calculate the value of E. So it is a type 1 low pass Chebyshev filter. Okay, so what is the formula for type 1 Chebyshev filter? Chebyshev filter type 1. So order of that filter n is equal to log in brackets 1 minus del square plus root 1 minus del square 1 plus e square, right? And in brackets, then divided by e del 2. Then this bracket closed, divided by log omega s divided by omega p plus root omega s divided by omega p whole square minus 1. It is under the root. Okay, so these are the, so omega s and omega p is given Now we have to calculate the value of del 2 and E. Okay, so how to calculate? So 10 log 1 plus E square is equal to 1 because 1 dB ripple in the pass band. Okay, so from here you can calculate like log 1 plus E square divided by 1 by 10 equal to 0.1. So 1 plus E square you will get 10 to the power 0.1 and E you will get 0.502. Okay, so directly here we can calculate E square also. E square is 0.259. Okay, now 20 log del 2 equal to minus 40 dB because the attenuation is 40 dB. So from here if you calculate del 2 you will get 0.01. Okay, and omega p already we know that is given as a cutoff frequency 1000 hertz, pass band cutoff frequency, and omega s is given as a 1500 hertz. Okay, now put all these values in this equation. So just I am putting all those values, then calculate it. Using the calculator. Okay, so log 1 minus del square. So del value is 0.01 square plus root 1 minus 0.01 square. 1 plus e square value is 0.259. Okay, and divided by this, I think whole divided by e means 0.502 into del 2. So 0 multiplied by 0.01. Okay, so it is a numerator part, and denominator part we have log omega s means 1500 hertz divided by 1000 hertz plus root 1500 hertz divided by 1000 hertz whole square minus 1. Okay, now just take calculator and calculate all those values. You will get log 393.042 divided by log 2.618. That will equal to, we will just calculate 6.205. That, and it is equal to 7 also, or 6. So just check in the answers and also just go through the calculation and check once I have got these values, and you can, so from here option A is the correct answer, but the given is option 4, option C, that means that coming is 4, but it is I think wrong because I'm not getting. Okay, so just check with this question once, just taking the calculations on this. Okay, so okay, I hope you are getting. So moving to the next question. The next question is convert the analog filters with system equation 2 into a digital IR filter, means impulse invariance method where sampling frequency is given 500 Hz. So using impulse invariance method we have to just change it into a digital domain. Okay, so equation is given, fs is given. So from here just first we need to calculate the poles and then convert it. HA of S given, first Fs is given, Fs is 500 Hz, Ts is 1 by Fs, So from here we will get 2 into 10 to the power minus 3 ts. Okay, now just from here poles we can calculate poles. S square plus 2s plus 3 is equal to 0. So S1 and S2 you will get, so minus b square from here, so you will get minus 1 plus minus 1.414 J. Okay, now HA of S poles we have got, so S divided plus 1 divided by S plus 1 minus J 1.414. Similarly, S plus 1 minus, plus J 1.414 you will get. Now just do that partial fraction and get the values of A and B. Minus J 1.414 plus B divided by S plus 1 plus J 1.414. Now if you just take a partial fraction and you will calculate, so A is equal to B is equal to, you will get 0.5. Okay, so just calculate it once, you will get it. Okay, now I am just putting all those values. HA of S is equal to 0.5 divided by S plus 1 minus J 1.414 plus 0.5 S plus 1 plus J 1.414. Okay, so no, already we know that. Okay, A plus J omega, it is something, right? So if you compare with this one, 1 plus minus say 1.414 in both the poles, so A value you will get 1 and omega value from here you will get 414, right? And also we know that omega t, right? We need, so 1.414 into 2 into 10 to the power minus 3. So if you further do that, you will get 0.00282. Okay, why? Because we are just converting into this into a z domain, then we will need all those things. Okay, so already we know that if you convert it of z, so that is equal to 0.5, that is 1 minus e to the power pt. So e to the power that value, so 0.0028 j z inverse we have calculated before that, plus 0.5 1 minus e to the power minus 0.0028 j z inverse. Okay, one is minus and one is plus. So if you just simplify it, we will get option A is the correct answer for this question. Okay, okay, so I hope you are getting. So moving to the next question. Now next question is also convert the analog filter with system function in equation 3 in this equation into a digital IR filter by a bilinear transformation where sampling frequency is given as a 1000 Hertz. Okay, so here it is given, the system transfer function is given, and by using the bilinear transformation we have to convert it. So I am taking this new. So given data is transfer function that is HA of S is given S plus 1 divided by S square minus 4. So using bilinear transformation. So already we know that in bilinear transformation, in the place of S we have to put the value of 2 by T 1 minus Z inverse divided by 1 plus Z inverse. Fs is given as a 1000 Hertz. From here Ts we can calculate, that is 10 to the power minus 3. So from here we can calculate 2 into 10 to the power minus 3, 1 minus Z inverse divided by 1 plus Z inverse. So that is equal to 2 into 10 to the power 3, 1 minus Z inverse divided by 1 plus Z inverse. Now put into the in this place. So 2 into 10 to the power 3, 1 minus Z inverse divided by 1 plus Z inverse, right, plus 1. Similarly, in the denominator also 2 into 10 to the power 3, 1 minus Z inverse, 1 plus Z inverse minus 4. It is a whole square, right? So now further what we need to do, so just they have asked same, but in the not in the form of Z inverse, they have given in the form of Z only. Okay, so what we need to do, just 1 by Z it is, so Z, so 2 into 10 to the power 3, so Z minus 1 divided by Z plus 1 plus 1, because that lower part Z will be the cancelled out. Now here 4 into 10 to the power 6, or you can we can write it to the power 3, 1 minus, just a minute, sorry, Z minus 1, Z plus 1 whole square minus 4, because they have asked in the same form. We don't need to convert it. Okay, so just 1 by Z and just all those things are cancelled out. Okay, so which option is correct? From here you will see option B is the correct answer for this question. Just check with the answer. Okay. Okay, so option B is the correct answer for this question. Now moving to the next question. The next question is, if h of s is equal to 1 by s square plus s plus 1, represent the transfer function of a low pass filter Butterworth with a pass band of 1 radian per second. So this transfer function has a pass band with 1 radian per second. Okay. Then what is the system function of a low pass filter with a pass band of 10 radian second? Okay, then what will be the system transfer function with the 10 radian per second? Okay, so to solve this type of question, so we will use the scaling. This problem. So to solve this problem, we need to scale the cutoff frequency. Cutoff frequency, that is 1 radian per second, in this case 1 radian per second to 10 radian per second. So that means S is equal to S by K, where K is equal to 10, right? So H of S is given as 1 by s square plus s plus 1. So just scale by this factor, s by 10 square plus s by 10 plus 1. Okay, so now 1 divided by s square by 100 plus s by 10 plus 1. Now 100 divided by s square plus 100, so here it will left 10s plus 100. So new cutoff frequency with pass 10 radian per second, the system transfer function will be the s square, 100 divided by s square plus 10 by 10s plus 100. So option A is the correct answer for this question. Okay, so in this type of question, if transfer function is given, but here it is a 1 radian per second, it is a cutoff frequency. Okay, if you see the low pass filter, it is a transfer function of a low pass filter, and this is a cutoff frequency of that low pass filter. Now what we need to do, we need to design a other system transfer function with the different cutoff frequency. So just we need to scale the cutoff frequency. Okay, so here the first cutoff frequency 1 radian per second, we have to replace this by 10 radian per second. So for that we need to scale s, value of s. So we will replace s to s by k. K is the scaling factor, but here k is given as a 10. So just put s by 10 in that same equation and you will get it. Okay. Okay, so I hope you have got this question. Now moving to the next question. Now next question is, when sigma is equal to 0, then what is the condition on R? Okay. So to solve this question, it is a S domain to Z domain conversion question. So as we know that Z is equal to EST, right? And already we know that S is equal to sigma plus J omega, right? And already we also know that Z is equal to R e to the power J omega, right? Now put these values. So Z is equal to J, so e to the power st must be equal to the e to the power J omega, right? Now put the value of sigma plus J omega t, right, is equal to R e to the power J omega. Here they have said sigma, put sigma is equal to 0. So what left? Sorry, e, here it is. So e to the power J omega t is equal to R e to the power J omega. So if you compare it here, so here nothing is there. So that means 1 is there, that cannot be 0. So R is equal to 1. And if you compare that one, omega t is equal to omega, the relation between analog to digital frequency. So if sigma is equal to 0, then R will be equal to 1. Okay, so this is the condition. If sigma is equal to 0, then R is equal to 1. Okay, okay, so I hope you have got this question. Now the questions come to end. So for this week, these are the questions. So if you have any doubt now, you can ask. Otherwise, we can close this session. Okay. Okay, so nobody has joined this class. So I hope no doubts is there. If you have any doubt, you can ask in the next class. So, okay. Thank you everyone. Thank you for joining this session. Now I am closing this session. Okay. So thank you everyone. Thank you for joining this session.